Hey, I just wanted to quickly plug that if you guys want any tutoring, some new slots have opened. If you look in the description, there's a link to my physics and maths tutor profile in which I do tutoring on there. Hello, everybody. Welcome back to another episode of the A-Level Cookbook. Today, we're going to be doing the AQA A-Level Chemistry Paper 1 from 2022. So let's get this bread. So this question's about equilibria. Give two features of a reaction in a dynamic equilibrium. So every single equilibria you know is this and this. So you can go that way, or you can go this way. Now, the interesting thing about equilibria is that eventually, if you leave it, everything sort of has a very set concentration and they all balance out nicely. So that doesn't mean that the concentrations are equal, it's just that they're not changing anymore over time. So what that means is that for them to be sort of like, not going from here and here, like, not for their concentrations not to change significantly, the rates of the forward and reverse reactions have to be equal. So forward, that's a bit thick there, pen. Let's make it a bit thinner, shall we? And reverse reactions have equal rates. You cannot just say they are equal because they're not. That doesn't tell them you mean rates. It just tells them that, oh, the reactions are the same, which is not correct. So then, as well as that, in an equilibrium, the other thing is that the concentration of reactants, reactants and products are constant. That does not mean they are the same. They are not. They are not the same. So if this and this make this and this, and it goes backwards, you might have like 10 of this and like one of those, and like 6 of these and like 4 of them or whatever, right? That's what it means. Is that this 10 will always stay as 10. It doesn't mean that this and this are the same because that doesn't work. It's not how it goes. So a gas phase reaction is at equilibrium. When the pressure is increased, the yield of the product decreases. So instead of trying to be like, giga gigantic brain trying to figure out an answer, just have a sec to think. It's telling you you've got this equilibrium, and what's happening is that when you increase the pressure, the product on this side is decreasing. So that must mean that the equilibrium is shifting more that way. So then you need to think, okay, so when I increase this pressure, the equilibrium's going this way. So what do we know about pressures? So we know that like when you increase the pressure, the equilibrium will shift to the side with the lower moles to counteract the change. So if it's going this way, then that means that there's got to be lower number of moles here than here. So there's got to be a higher number of moles here. So that must mean that there is more moles of gaseous products than reactants. It has to be gaseous because like aqueous stuff and stuff aren't going to really be screwed around with the pressure. So carbon monoxide and hydrogen react to form methanol. 0.43 moles of carbon monoxide is mixed with this much hydrogen, and at equilibrium, the total pressure in this flask is this, and it contains this much methanol. Calculate in moles the amount of CO present at equilibrium, and then calculate the partial pressure of carbon monoxide in this equilibrium mixture. So what people do is they go a bit crazy and they look at this and they try and do all kinds of random calculations. So in chemistry, and this goes for biology, maths, physics, everything, if you do a calculation, you need to be able to say what you're doing it for and what you're going to do with it next. Don't just blindly work out moles, because what happens is people work out moles and this and that and this and that, blah, 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 especially in them like big titration questions. And then they don't even remember what the thing they calculated corresponds with. So every time you do a calculation, you should be thinking, what am I going to do directly next with this thing? And what does this belong to? So whenever you got these equilibriums, what they're trying to tell you is that they've started mixing these two together, and then at the equilibrium, we have this much methanol. So let's write this. Let me rewrite this equilibrium out so we can actually do some working out stuff here. So here, CH3OH. So they've told you that this is this. So let's deal with the start, and we'll deal with the end. So at the very start, they've told you that they mixed 0.430 moles. So start moles, I should say, and moles of carbon monoxide. And then they've told you you've mixed 0.860 moles of hydrogen. How many do we have of methanol? Give it a second to pause, have a pause, say the answer, and we'll see. So because the equilibrium's not been set up yet, it's 0 at the start. Then, at the end, they've told you that we've made 0.110 moles of this methanol. So all of this methanol can only have come from these two things. So that must mean that some of this has reacted with this to give you this. So what we'd do is we would work out how much we have left. So what you would do is you would subtract, well, there's a 1 to 1 of these. So that must mean that we've lost 0.110 moles of this. So at equilibrium now, for our carbon monoxide, we have 0.43 minus 0.11, which is 0.32 moles. Now let's look at our hydrogens. So this has gone up by 0.110. So this must have gone down by a certain amount. Now because it takes 2 of these to produce one of those, this must have dropped by 2 lots as well. So this would actually be minus 0.110 times 2. So then you would do 0.860 minus 2 lots of 0.110, which is 0.64 moles. Actually, to be honest, I don't think we actually needed to do that, but whatever, I'm just doing it anyway. So then, no, actually we did. So the question then says, so it says calculate the moles of the carbon monoxide present at equilibrium. Well, that's that there, that's done. Then it says calculate the partial pressure of the carbon monoxide in the equilibrium mixture. So we need to think, what are we going to do? Well, every single sort of gaseous equilibrium, if you add up all of them, it'll give you the total pressure, which they've told you is this. So total pressure is 250 kilopascals. Each one of these is going to take up a fraction of that pressure, a section of it. So we need to work out the mole fraction of the CO. So the mole fraction is just the proportion of this in total. So our mole fraction of CO is just going to equal its moles, 0.32, because they want it at equilibrium, divided by the total moles. So 0.32 plus 0.64 plus 0.110. If we do that, we get 0.32 divided by 0.32 plus 0.64 plus 0.110. We get 0.2991. I'll round it. Right? That's the mole fraction. Don't just calculate, because a lot of people get to this and they're like, oh, I don't know what I'm doing with it. This is the mole fraction of CO, so make sure you list that. The other reason I say this is because you've got examiners who will have marked like 8 million papers of absolutely scrawny, terrible handwriting, and they can't be asked reading your stuff. So make it clear that it's mole fraction of this. Therefore, the partial pressure of CO2 must be its mole fraction, the fraction of the whole thing, times the total pressure. So 0.2991 times 250, which gives you 74.8 kilopascals. So then it says, give an expression for the equilibrium constant Kp for this reaction. So it's going to be your partial pressures, because we're dealing with Kp pressures. So it's going to be PCH3OH. There's only one of them, so there's no power there. And then it's going to be P of all your reactants. So carbon monoxide, and then PH2. But because there's 2 moles of it, it's squared. So then it says a different mixture of carbon monoxide and hydrogen is left to reach equilibrium at a different temperature. Some data for this equilibrium is shown as follows. So you'll see that every single one of these questions, I mean this one doesn't, but every single one of them refers to temperature. Have a think as to why. Even though it's not relevant right now, think why. Well, it's because Kp, Kc, Ka, K, anything in the universe is only affected by temperature. Pressure, concentration, catalyst, none of those affect it, because the equilibrium will just shift to balance things out and you get the same proportion of everything again. Temperature is the only one that does, because it factors in things like the forward reactions, enthalpy, and the reverse, and so on. Some data for this equilibrium is shown. Calculate the partial pressure in kPa of the hydrogen in this mixture. So we know that the Kp. So rule number 1 of any calculation is rearrange everything in terms of algebraically first, then put the numbers in. Please. It is so hard deciphering what some people write sometimes. So we know that the equilibrium. So what I mean by that is, like, we know this equilibrium here is that we've got PCO PH2 squared. Don't put the numbers in and all that jazz yet. Just rearrange it for what you want. So they want you to find the partial pressure of hydrogen. So I'm going to multiply both sides by that. So we get PH2 squared, and that would be times Kp. But while I'm here, I'll also just divide by Kp as well. So we would get PCH3OH all over PCO times Kp. Right? So if you rearrange it like that, then the examiner can see this, give you the marks. Otherwise, if you write random shit and then you get something wrong, they're not going to see anything but just the random numbers that you've churned out, and you'll get no method marks. So there's that. And then because we want PH2, I'm just going to square root this whole thing. So you can either work it out here and square root it at that point, but I'm just going to do it all in one massive go. So it's the square root of PCH3OH, all divided by PCO times Kp. So then you can substitute your numbers. So PH2 is going to equal the square root of whatever the partial times that by 1.15 times 10 to the minus 6. Let's see what we. So then you should get 1947. Sorry, I should say 194.7. There you go. Done. Bish, bash, bosh. So now it says use the Kp value from table 1 to get the Kp of this following reaction. So the Kp value, I'm just going to scribble down, was what, 1.15 times 10 to the minus 6, right? And they've told you to do it for this and at temperature T, and then you get absolutely nothing else to work off of. So Kp only applies to a specific equilibrium or a specific reaction. So the reaction that this Kp applies to is you're going from CO plus 2H2 to this. So you know your Kp is going to be like your sort of the partial pressures of your reactants and the products. So they've specified an equation, compare it to the original, and see what's changed. Literally look at the page and see what's different. No fancy shit here. So I'm looking at this, it's that. If I look at this, we're going from CH3OH back this way. So it's actually the reverse of these things. So that must mean that this Kp's is going to equal this over this, which would be the products in our from the one above over the reactants, the other way around. So that must mean that because when you flip a fraction, you're doing 1 over that fraction, the Kp for this one must just be 1 over the Kp for the other. So 1 divided by 1.15 times 10 to the minus 6, sorry. I don't know why I put minus 6, I've just realized now, whoops. Would give you what you need. And if you do that, you would get 8.7 times 10 to the 5. So rather than sitting and memorizing, oh, well, if you've got the, whoops, and the units would still be, it would change as well, because this one's unit is kPa to the minus 2. You're doing 1 divided by kPa to minus 2, so it's actually going to be kPa squared. Alternatively, you could just make it, figure it out again. But yeah, like, instead of learning some crazy method being like, okay, well, from now on, every single equilibrium that is opposite has to be this. Just derive it like this. It saves time. It promotes understanding. Rhenium has an atomic mass of 75. Define relative atomic mass. Oh, man. Blah, blah, blah. It's, mean mass or average mass of one atom of an element compared to or relative to, or whatever you want to say, 1/12 of a carbon-12 atom. The relative atomic mass of a sample of rhenium is 186.3. Table 2 shows the information about the 2 isotopes of rhenium in the sample. So it says relative isotopic mass is that to be calculated, and then abundances. It says find the relative isotopic mass of the other rhenium isotopes, show you're working. So what I see is a lot of people jump straight to try and doing the end step first. What's the point, right? Don't do that. You should know that the mass roughly is the the isotopic mass times its relative abundance plus all the other isotopic masses times its abundances all over the sum of the abundances. So if they gave you percentages, then that should be 100%, but sometimes they don't. So in that case, they've told you that the mass of this thing is 186 point. So therefore, 186.3, the mass they've told you, must be each isotope's times by each other and self, divided by the relative abundances added up. So it's going to be 185 is the first one times 10, plus this mysterious one, which I'm just going to call x. So make sure you put that down somewhere so you remember what it is, times 17, all divided by 10 plus 17. So if we then tidy this up a little bit, that would be 186.3 equals 1850 plus 17x all over 27. So then you times both sides by 27. Don't just say, oh, I'm bringing this up and doing that down. You're timesing both sides by them. If you do, because I've seen mistakes where people just sort of bring things up and down and not realize that you can't do that all the time. So then you've got it, because you have to, if it was like, I don't know, this plus a, then it would be 27a as well. And people forget that you can't just drag that down there. There's another thing there. So just to be cautious, best practice, So that would be 5030.1 equals 1850 plus 17 x. So then you subtract both sides by 1850 to get rid of the 1850. So 17x equals 3180.1. Divide that by 17, and you get x equals 187.1, which is what we again said the relative isotopic mass of this rhenium. So it's 187.1. Then it says state why the isotopes of rhenium have the same chemical properties. No matter what it is in chemistry, if you have the same electron, I'm going to write E- because I'm lazy, but you write the whole thing, configuration, it will have the same chemical properties. So now we have a sample of rhenium is ionized by electron impact in a time of flight mass spectrometer. 185 Re plus ion with the kinetic energy of this travels through a 1.45 meter flight tube. The kinetic energy is that, where m is this, v is this, k is that, and it says work out the time to reach the detector, and there's the Avogadro constant. So every time I go through this with people, they immediately panic and don't know what to do because they're trying to follow a routine and the routine doesn't work. Routines don't work. You have to understand what you're doing. So instead of following a routine, actually just think for a second, what do they want me to do? And what are my clues to getting there? Just please, yeah? So they want you to find the time taken to travel this from the start to the end of the detector. So then we need to look, what do I have in this question that could give me clues? They've told you that Ke equals a half mv squared. This might be a clue. But then think again, what part of this maybe links to t? Well, v is the same as distance over time. Speed equals distance over time. So that's your link to t. That's your saving grace. You're going to probably use this to find the time. So then our clue here must be that the kinetic energy is going to give us the velocity, which will link to time. So you need to do that, otherwise you can't get anywhere. So I'm going to rearrange that to give me my v. So 2ke, because I'll get rid of the half, and then we're going to divide both sides by m. Divided by m equals v squared. So that must mean that v equals the square root of 2ke over m. So now we need to look, okay, well, in order to get v, we need to figure out the ke and the m. So they've told us that it has a kinetic energy. They've told us that ke is 1.153 times 10 to the minus 13 joules. But we need m. Now, m is the mass of the ion. So we need to figure out what the mass of the ion is in kilograms. And this is the bit that everyone slips up on. It doesn't say a mass very obviously, but it does, because it tells you that this is a 185 Re plus ion. That number is the mass number, which is the relative mass, blah, 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 compared to 1 to the carbon atom, blah, blah, blah. But these masses are all the mass of 1 mole of thing in grams. So what the units of this 185, if you should know, is a gram per mole. So every single mole of this will weigh 185 grams. That's what the mass number means. So because that's 185 grams per mole, that means that 1 mole of Re plus ions weighs 185 grams. Therefore, if we just want one singular Re plus ion, remember that 1 mole is 6.02 times 10 to the 23. So 6 times 2 to the times 10 to the 23 of Re plus ions gives you that. So one singular Re plus ion's mass must be 185 divided by Avogadro's constant, because that will give you what one singular ion would be. So that's 185 divided by 6.022 times 10 to the 23, which gives you 3.0721 times 10 to the minus 22. But there's two things. Don't just calculate blindly. Again, this is one Re plus ion mass, and this is in grams, because the unit is grams per mole for the periodic table stuff. So that means we need to convert that to kilograms. So all you do is you just divide it by 1,000. So that's going to be 3.0721 times 10 to the minus 25 kilograms. Now we have enough information to do the kinetic energy over m stuff. It's because now you know v squared, like we said before, is going to be 2ke over m. So that's going to be 2 times the 1.153 times 10 to the minus 13 joules. And that's in joules, so we don't have to do anything with that because it's in base units. All divided by the m, which is going to be 3.0721 times 10 to the minus 25. So that must mean that v squared equals, and if I just quickly work that out, so that's 2, 1.15 times 10 to the, 153 times 10 to the minus 13, all over 3.0721 times 10 to the minus 25. That would be 7.506 times 10 to the 11. And then obviously we want the velocity not squared because we just want v, so that's going to be the square root of that. So it's going to be 866,387, blah, 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 blah. So we know that speed equals distance over time, and they want us to find time, so then vt equals so t equals d over v, which is going to be, and they've told us the distance is what? Where is it? 1.450 meters, 1.450, and then we divide it by that velocity we just worked out, 866, blah, 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 blah. And if you do that, you get 1.450 divided by your answer. It should give you 1.67 times 10 to the minus 6. So 1.67 times 10 to the minus 6. So don't just sit and learn a routine, please, for the love of God. Look at what you've got in the question and work backwards and look at what the puzzles or the pieces of the puzzle. It always hinges on v equals dt to link this and the time or the distance or the length. Don't just sit and be like, okay, so I've got to do this step, this step, this step. Like, just think for a second. The key thing to always remember is that 185 or any mass number is in grams per mole. Or, if you do it like this way, I guess, as well. So that means that 1 mole of whatever it is will weigh this much in grams. So then it says, state how the relative abundance of this is determined in a time of flight mass spectrometer. So you need to think, what is the in a time of flight mass spectrometer? Everyone loves saying electron ionization, this, that, blah, blah, blah. Think of every reason as to why those steps happen. So the first electron gun impact, or the electrospray ionization bit, is to ionize it, because it wouldn't move through the electrical fields and all that kind of stuff if it wasn't charged. If you have an electrical field, it's positive and negative here, and it's uncharged, it'll just go like that. Whereas if you got like a positively charged thing, it's going to bend like that. That's the whole point of that first step, and then moving through the electric field. It's got nothing to really do with those. Those are just all prep. The relative abundance is to do with the fact that they actually get detected and how quickly they're all getting detected. How many of them are passing in a second, the current. So what it is that the detector, the R plus ions, gain an electron because it's a negative plate, or the detector's negative. The detector, it's a negative plate. That's what happens, and then the relative abundance depends on the size of the current, because a current is a flow of electrons. So if these are all hitting them and they're gaining electrons, and that's loads and loads of electrons being moved, flowing through a current to these. So what it will do is it'll measure that current and then spit out a number based on like lots of different other factors as well that calibrated that are way beyond the chemistry A level. But that's actually how it's determined. All the rest of the steps are just prep. Cool. So then next one we have is, this question is about hydrogen peroxide, H2O2. The half equation for the oxidation of this is that hair bleach solution contains hydrogen peroxide. A sample of hair bleach is diluted with water. The concentration of hydrogen peroxide in the diluted solution is 5%. The original solution at 25 centimeter cubed of the dilute bleach solution is acidified with dilute sulfuric acid. The acidified sample is titrated with this much potassium manganate solution. The reaction is then complete when this much potassium manganate is added. Give an ionic equation for the reaction between potassium manganate and the acidified hydrogen peroxide, and then calculate the mole per decimeter cube concentration of hydrogen peroxide in the original hair bleach solution. So these questions are purposefully like this to test your reading comprehension skills. If I say cats are animals, and then I say cats have 4 legs, can you say that every single animal in the world has 4 legs based on this text alone? No, because I've not said that. I've just said cats are animals, but they also have 4 legs, 2 separate traits. So what happens is with this stuff, dude, is that people just keep bloody calculating God knows what. I don't know what they're doing. I don't know why they're working out stuff. They're like, the moles are this and this and that, and it's just like, just give it a sec and calm down, yeah? Please. So literally what I do, and I'm going to do that because I can't do this question if I don't, is write a little flowchart of what's going on. So what they've done is they've just got they've got H2O2, they've got hair bleach. So let me find some space that's a bit more, make it a little bit tidier. So they've got hair bleach, and what they did is they diluted it. So what did they do? So it's to 5% of original. All right. Then what did they do? They took 25 centimeters cubed of this. And what did they do? They titrated it. So, and they don't just write titrated with, that's useless. Like, say to yourself what's going on. Reacted with potassium manganate, so KMnO4. And then they said the concentration of this KMnO4 is 0.02 mole decimeter cubed. And they've told you that the reaction's complete when this much has been added. So that means that this reaction was complete when they added 35.85 centimeters cubed of it. So what that means is 35.85 centimeters cubed of this KMnO4 reacted with 25 centimeters cubed of this mystery hair bleach solution that we had. If you just take a second to get what's going on here, then your life will be a lot easier. Otherwise, you're just going to hate your life and it's just not going to be great. Okay, so they've told you that we've got the potassium manganate reacting, and it's from 7. And they've told you that this is being oxidized. So where something is oxidized, something else has to be reduced. So I'm going to just quickly derive the potassium manganate thing, the half equation, because I just don't commit it to memory, because, like, why? I could just take a quick second to derive it again. You can if you want, but I just don't, because I don't want to. So MnO4 minus, we know it's going to end up becoming, well, if it's being reduced, the only other form that you should know about of existing is Mn2 plus. So look at the oxidation states of the Mn. So this is O4 minus, that's minus 8, but the overall charge is what, minus 1, so that's going to be plus 7. And then here it's, well, 2 plus, so you know it's plus 2. So that must mean that this whole counter must mean that we've also got, give me a minute, MnO4 minus, so we need to be adding 5 electrons on this side, adding to this to get to there. Then what we do is we make sure all the elements that, that are interesting are balanced. So we know that Mn is balanced on both sides so far. Fine. Next, we need to balance our oxygens. So the only way to add oxygen is by water. So we need 4 oxygens. So that means we're going to have to add 4 H2Os here. But then, now we don't have any hydrogens on this side and this side. So what we do is we add the number of hydrogens we need to get here. So that's going to be 8 H pluses. And then you just double check the charges add up. So that's what, 5 minus 1. That's what, 6, 2, plus 2 overall, plus 2 overall. Satisfied. Cool. Then they've given you the equation up there for hydrogen peroxide. They've said that H2O2 goes to O2 plus 2H plus 2E minus. So the reason I'm doing that is because we know that this mysterious hair bleach solution has hydrogen peroxide, which has reacted with KMNO4. So we're doing this so that we can work out what the actual equation of these two things is to do the rest of the steps. So we need to balance the electrons to combine them. So what we're going to do is we're going to times U by 5, and we're going to times U by 2, and then combine them. So if we do that, we now have 10E minus plus 2MnO4 minus plus, MnO4 minus plus 16H plus goes to 2Mn2 plus 8H2O. And then we're also going to have 5H2O2 goes to 5O2 plus 10H plus 10E minus. When you combine the two, anything that's on both sides goes away. So in combination, you would get, I meant to write there for, you get 2MnO4 minus plus 5H2O2. So that's that sorted out. I like to underline them as I go along just to make sure. So that's that and that. The electrons are they can be gone now because they're on both sides. We have what, 16H pluses here and then 10 here. So then the amount of H pluses we have left must be 6H pluses. So 6H plus, because 16 here, but there's still 10 there. So that's that and that dealt with. So we get 2Mn2 plus, which is dealt with here. What else have we got? Plus 8H2O, dealt with, plus 5O2. There. So now we've got our overall equation, which, as we remember from before, is the titration between the two of these. So now we can, what do they want us to do? They want us to work out the concentration of the hydrogen peroxide in the original hair bleach solution. So, well, we now know we have this reaction equation. We now know that the concentration of KMNO4 is. This KMNO4 is going to dissociate into Ka plus and MnO4 minus. So we can work out the moles of MnO4 minus using this. Again, you want to write the moles of MnO4 minus. Don't just write moles, write out what it actually is. So it's going to be concentration times volume, which is 0.02, times its volume, which is 35.85, divided by 1,000, which gives you 7.17 times 10 to the minus 4 moles. Remember, what am I going to do with this directly? Where does it belong to? So this belongs to this in this equation. We want to find hydrogen peroxide, which is this. So the moles of H2O2, well, you can see there's a 2 here and there's a 5 there. So it's going to be this, your answer, divided by 2 times by 5, which is going to be 1.793 times 10 to the minus 3. So then, it's asking you what the concentration of the original bleach solution is, but remember, we took 25 centimeters cubed of this mysterious sample and did the reaction. So in order to go backwards to the hair bleach original solution, we need to work out what the concentration of the sample is. So the concentration, so I should say, what's the H2O2 concentration is going to be its moles, so 1.793 times 10 to the minus 3, divided by the volume of this sample that we have. So it's not the whole reaction mixture, because it's gone. So if it's reacted fully, that's disappeared. But we're not. We're doing this as in its pre-reaction, so it's going to be 25 divided by 1,000. Because we took a 25 centimeter cube sample, which is 0.0717 moles per decimeter cubed. But that's not it, because we want the original concentration. Well, they've told you that we diluted it to 5% of its original concentration. So this is going to be 5% of it. So to work out 5%, it would just be 0.05 times the original concentration. So I'm going to call it X. So in order to get the other way around, X, the original concentration, will be 0.0717 divided by 0.05. If you do that, you get 0.0717 divided by 0.05. That gives you 1.434. Or alternatively, if that's 5%, to get back to 100, you can times it by 20. But there you go, 1.43. So then it says, state why an indicator is not added in this titration. Well, think about what's going on. Indicators are used to help you figure out when the reaction ends. So we're using KMNO4. Well, it goes from colorless to pale pink. So the KMNO4 itself is an indicator. Whoops, KMNO4 itself is an indicator. It says give the oxidation state of oxygen in hydrogen peroxide. So you've got H2O2. Now the issue is that everyone knows this is -2, right? But if that was -2, that'd be -4, and then you'd have to have +2 here, which is not really possible because you can't take any more than one electron away from the hydrogen. So these have to be +1s, which would give you a +2 in total. So these have to actually be -1. Next, it says hydrogen peroxide decomposes to form water and oxygen. Give an equation for this reaction, and then calculate the amount in moles of hydrogen peroxide that would be needed to produce this much and whatever, blah blah blah. Right? So a lot of people shit themselves because they're trying to do it sequentially. Just work with what they've given you first. They told you hydrogen peroxide, which is that, decomposes to form water and oxygen. Right? There's no need to add any extra elements, and all the elements we want are here. So now it's just a case of balancing it out. Well, we've got 1, 2 oxygens here, but 3 there. But, there's 2 here. So let's try and make the numbers balanced. So if I make this 2, that means I have 1, 2, 3, 4 oxygens here, and then 1, 2, 3, 4 hydrogens. There's 4 of them. So if I put a 2 there, that's 4 hydrogens, and that's your 2 oxygens. Sorry, that's 2 hydrogens. That's the 4 oxygens sorted. Next, it says calculate the amount in moles of the hydrogen peroxide that would be needed to produce this much volume at a gas of this and this and this. Right, cool. So we need to use, because they've given us the kind of gas constant as well, it kind of gives it away. We're going to have to be using PV equals nRT. Ideal gas law. Now, the problem I see is that people, first of all, don't rearrange it to look what they want for, and they also just don't know what they're talking about when they're doing this. And they're calculating all kinds of random stuff. This applies to whichever gas you choose. So if this is a gas, then this PV equals nRT is this, applies to this. And this one's numbers would apply to this and so on. So you can't mix and match. You can't use values from this in here and then values from this in here. That's not how it works. Whatever you put in this is going to be what it is. So first of all, we want to find out the moles of hydrogen peroxide. So we want this. What have they given us? Well, they've given us the volume of the oxygen gas, its temperature, the pressure and temperature. So we're going to have to use the moles of the oxygen to work backwards of the hydrogen. So don't learn routines. Think about what's going on. So PV equals nRT. Let's rearrange it to get what we want. So that means that PV over RT would equal N. I'm dividing it by R and I'm dividing. So, but again, we're going to work out the N that we want. So we're going to work out the N of the oxygen, not just mix and match. Moles on its own isn't going to do enough. So then if we work out the moles of the oxygen, it's going to equal the pressure, which is 100 kilopascals. But remember, we have to have it in standard units, so it can't be kilo, it has to be just pascals. So it's 100,000, right? Times the volume. So where's the volume? They've told you it's 185 centimeters cubed. It has to be in standard units. So it's the base units. It can't be centimeters, it has to be meters. So the way I like to think of it is that if we think about it this way, so 1 meter is 100 centimeters, right? You times by 100. 1 meter squared should be 100 of these squared. So you times by 100 squared. So 1 meter cubed is going to be 100 cubed. So you would times it by 100 cubed. So if we're going from centimeters cubed to decimeters cubed, it's going to be its volume divided by 100 cubed. So it's going to be PV. So it's so PV times 185 divided by 100 cubed, or divide by a million if you want, over RT, which is 8.31 times the temperature, which is 298 Kelvin. Because this only works when it's in Kelvin. So if we do that, it's 100,000 times 185 over 100 cubed, 8.31 times 298. That gives you 7.47 times 10 to the minus 3 moles. But again, don't just blindly calculate it. Think, what am I going to do with this next? What does this belong to? This is the moles of your oxygen. So that must mean, if you look at the equation, the moles of H2O2 must be 2 times your answer, which is 0.0149 mole. So then it says hydrazine is a rocket fuel that's oxidized by hydrogen peroxide. The equation for this is this. The enthalpy change for this reaction is that. So here's some mean bond enthalpy values. Define the term mean bond enthalpy. Use the equation in the data to calculate the value for this. So I low-key hate it when people do the whole, oh, I'm going to do the energy, the bonds made, bonds broken thing. I think that's BS. I think you can just do Hess's law cycles for literally all of these. It's easier. it's more reliable. You'd screw up less, and also like it means you have to know what the definitions are and actually apply them. So rather than just sitting there and being like the definition is this or this or this, actually think what it means. So the definition, it's bond enthalpy. So it's going to be the enthalpy change. I'm going to write delta H because I'm lazy, but you write the whole thing. When? Well, what you need to say what it is. So it's the enthalpy change. Sorry, to break 1 mole of bonds averaged over a range of compounds. So it's not that they're like learning for shits and giggles what the actual enthalpy changes are. It's so you understand what the enthalpy changes actually mean. So if we look at the bond enthalpy, so I'm gonna write bond and just for short. What I like to do is with all of these, I like to think just generally in basic terms. What do we start with, or what do we finish with? So if we're breaking 1 mole of bonds, we have bonded stuff breaking down into atoms or elements, and all that stuff. So, for example, another example, I guess, is if we look at enthalpy of formation, right? Everyone's like, oh, it's when 1 mole of a substance is made from its constituent elements in standard state, blah, 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 blah. That's great and all, but they don't actually know how to use it or what that means. If it's 1 mole of a substance is made, so you've got 1 mole of a substance here made from its elements in their standard states, then any equation that's an enthalpy of formation will look like the element to the substance. In the same way, the enthalpy of solution is where you go from 1 mole of a solid ionic compound to its aqueous ions, dissolved in any blah 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 blah. You would have aqueous ions, solid ionic lattice. So the reason I'm saying this is because you can use these in these tables to work out a cycle and how you draw them. My advice is stop learning enthalpy of formation goes up, combustion goes left and right and up and down, all that. It doesn't work because they'll give you one that you don't know and then you're screwed. Because they do that every time. You can't use routines. So this is what I recommend you start doing and stick to doing, and you'll never ever get a question like this wrong. So rule number 1 is write out the overall equation again, just generally. So I'm just going to quickly scribble it down so I have some space to work with. So 2HOO. You'll never catch me doing bonds broken, bonds made BS, dude. I hate it. So, give me a minute, and then plus 4 lots of HOH. Now, you then look at the question, and it's telling you that the enthalpy change for this reaction is minus 789 kilojoules. So they've told you that this. Why is the pen not changing? They've told you that this thing is going to be minus 789 kilojoules per mole, right? So as long as you start with these two and you finish with these two, it will always be minus 789 kilojoules per mole. That's what Hess's law is. If you start and finish at the same point, doesn't matter how you get to that, it's the same. So then what you do is you look at the table and you think, what enthalpies have they given me? So they've given me the mean bond enthalpy, which we said is where you break 1 mole of this and that. That's great and all. But think of it just in logical sense. You've got bonded stuff breaking into atoms. Or so bonded stuff, or your elements, you could say, if you want to. Right? It's just broken down into nice little pieces. So what you then do is you look at your equation and you think, which of the enthalpy reaction that I've come up with in general terms do I have in the equation? So is this the bonded stuff or is this the atoms? So this is bonded stuff because the enthalpy of the mean bond enthalpy is being applied to this to break it down. This is the bonded stuff, that's the bonded stuff, that's the bonded stuff. So in my cycle, what must be at the bottom is my elements or your atoms, which you can write down, but I'm lazy and I do this. Then you need to decide which way the arrows go. Well, they've told you the mean bond enthalpy, which is again going from bonded stuff to atoms. This is the bonded stuff. And the other B is from bonded stuff to atoms. So the arrow goes down like this in every single one, because these are bond enthalpies for all. If the question gave you enthalpies of formation, you know that's 1 mole of a substance being made from their standard states, blah, 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 whatever elements, but whatever you want to say. The enthalpy of formation is from elements in their standard states to the end product, which would be upwards. That's why it goes up. So rather than sitting and learning, up and down, do this. Then what you do is you just fill in the numbers. So then you've got to put the numbers in. So we know that there's 388 here, plus 4 lots of NHs. Sorry, not 388. We have a 163 here, so 163 plus 4 lots of the NHs, so that's 388. And then what you've got is you've got 2 lots of this, but then you've also got 2 as well, so you've actually got 4 lots of 463, because there's 2 here, 2 here, and then we've got an OO as well, so that's going to be, oh well, they don't know what the OO is, do we? So that's going to be OO. Then we have an N triple bond N, which is 944. And then we've got 4 lots, but 2 of them. So it's going to be 8 lots of 463. Then what you do is, again, if you go around this cycle, it's going to equal the overall's reaction because we're starting and finishing at the same point. So that must mean that the overall enthalpy, so minus 789 equals this way, but then obviously because we're past this arrow, you're going back up. So if you follow an arrow, the sign stays the same. If you go against it, the sign flips. So that's going to be 163 plus 4 lots of 388 plus 4 lots of 463 plus the mystery bond we want because we're going against this arrow now. It's going to be minus 944 minus 8 lots of 463. Then what you do is just tidy it up. So minus 789 equals, so just add up all your bits and bobs. So 163 plus 4 lots of 388 plus 4 lots of 463 minus 944 minus 8463. So I'm just adding everything up that can be added up and leaving the unknowns out. So that's 1081 plus the 00 bond that we want. So that must mean that the 00 bond must be minus 789 plus 1081. So if we do that, we get minus 789 plus that, and it gives you 292. 292. However, this is 2 moles of it. Yeah, I should have actually written that up there. Sorry, whoops. There's 2 and there's a 2. So that means that the 00 is half of that, which is 146. Because the definition says it's where you have we're breaking 1 mole of bonds averaged in a range of compounds. So because we're breaking 2 moles of these now, it should be double that, if that makes sense. So you should really, really just Hess's law cycle all of this. And this carries on to Born-Haber cycles too. Born-Haber cycles are all just Hess's laws on crack. Everyone loves to be like, oh, well, this is the other bit formation, and everything else is the equal as a result, but never actually think why. Well, you're starting with, its elements in its standard states, and you're making the solid ionic compound. But if you go around this way, you're still starting at the elements in their standard states, and you're still making a solid ionic compound at the end. So if you start and finish at the same point, you get the same thing. That's why this stuff works. So Hess's law, please, if you can, because it literally never fails you, no matter what you do. Okay, right. So acids and bases, one of my favorite topics. So it says here, this question's about acids and bases. Calculate the pH of this ethanoic acid at 25 centimeters cubed and give your answer to decimal places. So first of all, strong or weak acid. This is a weak acid, so it partially dissociates. So we can't just go ahead and say that the concentration of this is the same. So we're going to have to use Ka. But the issue is we don't know which Ka to use, because you've got your Ka equals H plus A minus over HA. And you've got your other one, which is H plus squared over C, HA. Well, I was going to write the actual acid here, but HA here. So which one do we use? Well, it's important to look at the equilibrium and think about what's going on in it and understand what each of the letters mean rather than just vaguely saying stuff. H plus, protons, that's all we care about when it comes to pH. We want to find that. HA is your concentration of your acid. H plus is what makes your protons. It's what makes an acid an acid. So then A minus, what does that mean? Where does that come from? So A minus is obviously the bit from there, but what provides it? So remember, because the equilibrium in this is so far to the left, there's barely any A minuses, and this is pretty much the same. So this A minus, when you see it in an equation, actually represents the salt. Not the base, because if you mix an acid and a base, what happens? Acid plus a base makes salt plus water. So that's not the base. Obviously, the base can go on to make it, and it could be the same amount, but that's not base objectively. What base is your OH minus. That's representing bases. So whenever you see an OH minus, base, A minus means salt. If you think of it as basically as that, this whole topic becomes a lot easier. So the question's told you've got this solution of ethanoic acid. Is there any salt in it? No salt, so there's no this, so it's this equation. So that means that we've got Ka equals H plus, so equals H plus concentration squared over HA. Don't put your numbers in now, rearrange it first. So Ka, HA, and then that would equal H plus squared. So I'm going to square root that, and that gives me my H plus, which would be the square root of 1.74 times 10 to the minus 5 times the HA, which is 0.150, which gives you 1.62 times 10 to the minus 3. And then pH equals negative log to the base 10 of the H plus, which would be negative log base 10 to this of this answer, which gives you 2.79. If you think of things, if you think of this topic as basic and as obvious as that, what you see is what you do and what you get and so on, then it gets a lot easier. There is no OH minus in this, no base. There is no salt in this question, and A is salt, so it's not going to be the one with A minus in it. And even if you tried it, you wouldn't get to the point where you could do it because you don't know what A minus is. So, you might as well save yourself that. Strontium is an element in group 2. You may so calculate the pH of 0.1 mole per decimeter cubed of strontium hydroxide at 10 degrees Celsius. You can assume that strontium hydroxide is completely dissociated in this. So rule number 1 is to figure out what the hell strontium hydroxide is. It's in group 2, so it's going to be Sr2 plus OH2. So when it dissociates, it's going to form Sr2 plus 2OH minus. So it's told you that it's completely dissociated. So that must mean we can we can say that if this is 0.0100 moles per decimeter cubed of this stuff, then we must have 0.0200 moles of OH minus. So the concentration of OH minus has got to be double that, so 0.02. Yeah? Then what we do is we need to find the pH. Every time you want pH, you want H plus. So you need to think, what do I know of that has H plus and OH in it in the equation? So that's Kw, which is H plus OH minus. Rearrange. That's the base, and this is a base. So then Kw over OH minus will give you your H plus, which is going to be 2.93 times 10 to the minus 15 divided by the OH minus we just worked out, which is going to be 0.02, which is 1.47 times 10 to the minus 13. And then that's for your H plus, remember? So then if you negative log to the base 10 of that, you get 12.83. So again, you didn't have to dig out some crazy method or whatever. It's just literally look at what's on the page and then think, what do I know that does this? So I found out like this was OH. I want to find H plus. What do I know that links H plus and OH minus together? So the pH of a barium hydroxide solution is lower at 50 than at 10. At 50 degrees Celsius, a 25 centimeter cube sample of this barium hydroxide was neutralized by 22.45 centimeters cubed of hydrochloric acid added from a burette. To reduce the volume of the hydrochloric acid that should be added from a burette to neutralize another 25 centimeters cubed sample at this and explain your answers. So again, 25 centimeters cubed of barium hydroxide needed this much, right? And then it's saying, well, if you got another 25 centimeters cubed of that barium hydroxide, how much would you need? Think for a second what's going on. If we're neutralizing, what's the reaction that happens in neutralization? Have a think and then tell me. Well, don't tell me because you can't speak to me, but have a think and then come back. So neutralization is H plus OH minus gives you H2O. So if we have a 25 centimeter cubed of barium hydroxide, we're going to have the same amount of OH minus because the only thing that's changing is the temperature. So the volume has to be the same because that's how many H pluses you needed the first time around in the first part of the question to neutralize them. So you've got the same number of OH minus ions. So you didn't have to go and learn a separate fact being like, okay, well, if you think about it this way, temperature doesn't affect this and that, blah, blah, blah. Like, why sit and learn an extra fact when you can just think for it? State how a buffer solution can be made from solutions of potassium hydroxide and ethanoic acid. Give an equation for the reaction between these two and then whatever. So any buffer in the universe, whether it's acidic or not, is going to be a weak acid or base mixed with its salt. So either you could react the acid with a base to make a bitter salt, but remember you don't want to neutralize the whole thing, so you have extra acid, little bit of base, or you could just mix the acid with its salt directly. So now they've told you that you've got potassium hydroxide, which is a base and acid. So an acid plus a base makes a salt plus water. But you don't want to get rid of all the acid, remember. You want a weak acid and its salt. So what you do is you mix excess ethanoic acid. I'm just going to write acid because I'm lazy. And with KOH. Why? Because then that will give you a mixture of the acid and the salt, and every single bit of that base that you've added, this KOH, will all eventually become the salt, which remember is A minus. So all of your A minus came from the OH minus originally that's reacted. So it's just really good to think of things like that in this topic. Then it says, well, write the equation for this. So ethanoic acid is CH3COOH plus KOH. So just have a think about what normal reactions happen. So HCl, NaOH plus HCl, right? You know it's NaCl and H2O, right? So an acid plus a base makes a salt plus water. So just do the obvious one. Sorry, whoops. That's supposed to be an arrow. It makes a salt plus water. So you know one of these has to be H2O. So this OH must have taken an H plus. It's accepted a proton. It's reacted with it to give you the H plus. So the H2O, sorry. So then whatever's left over has to be the salt, which is going to be this acid. Remember, because it donates a proton, it loses one. Because everyone loves saying proton donate, but they don't actually know what that means. CH3COO minus. And then it reacts with the K as well to give you K plus. That's your salt. Then it says, state how this buffer solution resists change in pH when a small amount of acid is added. So remember, when you have a weak acid and it's salt, it's always going to form this equilibrium. HA becomes H plus A minus, where the A minus is your salt now. And it will just keep doing that. So how resists pH change? Well, when you add acid, what are you adding? Have a second to just think what you would say. So adding acid is the same as adding H plus. So if we do that, what's it going to do? It's going to increase the concentration of increase the concentration of H plus. So what's going to happen if this goes higher? Well, like every other equilibrium, you guys know that it would shift to the left in this case. So the equilibrium shifts to the left. I know it says ignore equilibrium in the mark scheme, but you might as well just say it. Don't lose any harm. Shifts to the left to counteract this and lower pH back down to normal. But simply, in every equilibrium question, you can't just say it shifts to the left. You need to say what the shift means. So what that means is it's shifting to the left because it's reacting with that to make this again. But you can't just say A minus. You have to say what it is. So this is by H plus reacting with CH3COO minus, the A minus from the salt. And that's how it resists the change. Okay, so buffer solution is made by adding 2 grams of sodium hydroxide to 500 centimeters cubed of sodium ethanoic acid solution. Calculate the pH of this buffer. So again, with all of these, first of all, rule number 1 is figure out what you want to find. So you need to find H plus. We're using a weak acid, and now there's going to be a salt in it. So that must mean we've got to use the KAHA minus whatever, right? So let's scribble that one down. So Ka equals H plus A minus over HA. So what I do, because this is an equilibrium, we need to find out what everyone gets lost on this and thinks it's some crazy stuff. It is the same as every other question where it's like an equilibrium is set up by mixing these two together and this one just found an equilibrium. Same thing. It's the same thing. So here, what I'm going to do is I'm just going to call that that's my ethanoic acid. So I'm going to write my overall equation of what's going on here. So ethanoic acid plus your NaOH gives you, well, acid plus a base makes a salt plus water. And what I do is I label this as well. So that acid is going to be HA. Remember, NaOH is just OH. That's a base. The salt is what's going to be your A minus eventually. The water we don't care about. And then what I do is I do the start moles. I do the end moles. And remember, this formula wants concentration, so we need to do the end concentrations as well. So at the very start, what are they doing? They're reacting 2 grams of sodium hydroxide. Sorry, 500 centimeters cubed of this much ethanoic acid. So the moles of the ethanoic acid is going to be 500 divided by 1,000 times 1. So that's going to be 0.5 moles. Now, let's see how much NaOH you have. Well, we need to find the moles of the NaOH. So mass equals moles over mR because it's a mass. So it's going to be 2 over 40, which is 0.05 moles. All right, how many moles do we have at the start of this reaction when nothing's yet happened of salt? 0. How much do we have of water? 0. So then what we need to do is we need to figure out what's reacting. So these two are going to react as best as they can. There's an excess here of the acid than there is the base. So we're going to have all of this base is going to react. There's going to be none of it left at the end. So there's 0 base left. All of that base must have gone into making the salt. So that's 0.05. So if this has gone up by 0.05, that's dropped by 0.05, then that must mean 0.05s of these has dropped. So the moles at the end of this must be 0.45, this subtracted by this. But remember that we need our concentrations at the end. So the end concentration is going to be these over its volume, which is going to be honest, because the volume's not changed, you can actually just do this in terms of moles. But I just don't like taking the chance personally, because I know that I would screw something up. So if we divide that by 500 divided by 1,000, that gives us it's 0.45 over 500 times 10 to the minus 3, which is 0.9. There's no base left there, you would expect that. and then you would get 0.1 moles per decimeter cubed of the salt. People might just be like, oh, well, why don't you just remember that you don't have to do that then? You don't have to, all of this will eventually become that. It's like, well, maybe it might not. Maybe they might give you a question where they made the buffer wrong and you have to calculate it and say, oh, the buffer didn't work because they did it wrong. So, just no shortcuts. Ka, Ha, so we're timesing them together, dividing it by A minus will give us our H plus. So now we put our numbers in. So Ka, they've told you, is 1.74 times 10 to the minus 5 times our Ha, which we've now worked out to be 0.9, divided by our A minus, which is 0.1. That gives us an H plus of, let me just work that out real quick, so 1.74 times 10 to the minus 5 times 0.9 over 0.1 gives you 1.57 times 10 to the minus 5, sorry. So if we want to find the pH, a negative log to the base 10 of that, which gives you 3.80. If you follow this systematic method every single time, you will never, ever, ever screw up an acids or bases question ever again. It forces you to look at everything in order. This question is about period 3 elements and their compounds, which is not a correct statement about magnesium hydroxide. So let's have a look. It is used to neutralize stomach acid. Well, no, it can be. It forms a solution with a pH of 14 at 25 degrees. And it has an empirical formula of this. So it is that one. Enjoy. Okay, so the reason it's this is simply just because it's less soluble than if we had, like, for example, NaOH. So NaOH tends to form a pH of like 12 to 14. But because MgOH2 is less soluble, you would have a pH that is like 9 to 10 instead. So then it says, give a reaction with aluminium oxide sulfuric acid. So just start off by writing what you know. So you're gonna start with Al2O3. You're adding H2SO4. So what are we going to make? Well, we're going to make an aluminium salt. So Al2SO4 3. And we're going to make H2O, salt plus water. So then you got to just balance the bits out. So we've got our Als balanced out. How many SO4s do we need here? 3. So I'm going to put 3 there. And then how many H2Os do we need? 3. And that's it. Done. Identify a reagent or test that can be used to distinguish between aqueous solutions of sulfur dioxide and sulfur trioxide at the same concentrations, and then state the observation in each case. So sulfur dioxide and trioxide. What could we do? So there's multiple. You could use universal indicator, for example. You could use a pH meter. I'm going to say pH meter because I'm a bit more precise. So if you use a pH meter, then what's the difference? So again, sulfur dioxide, SO2 and SO3. So we need to think about what's happening when you've got these solutions of it. So when you have a solution of sulfur dioxide, you're adding H2O. It forms sulfurous acid, so H2SO3. And when you got SO3 and H2O, you're making sulfuric acid, H2SO4. So if we just take these acids and have a look at what's going on, H2SO3, H2SO4. So we know that this one will dissociate into 2H plus and SO4, 2 minus. And this one will dissociate into 2H plus and SO3, 2 minus. Which then we need to sort of distinguish what their behaviors will be like in terms of how much H pluses we get. And obviously we can see there's a 2 and a 2 here. However, this one is a stronger acid. So if it's a stronger acid, it means it dissociates more into this, so you'll have more of these. So if it's a stronger acid, then that means it's going to have, where are we, sulfur trioxide, its pH is going to be much lower. So it's around 0 to 1, whereas this one's pH of 2 to 3. Or alternatively, what you could do is you could use universal indicator. So this would be like orange to red. That would be more red. Or what you could also do is you could add like a metal carbonate. So like, for example, calcium carbonate. This will react less vigorously than this. The mass spectrum of the element phosphorus has a peak at MZ124. Give the formula of the species responsible for this. So all you got to do is look at the phosphorus, which is 31p, and have a think what's going on. Because normally on the periodic table it looks like that, but you got 124. So best bet is to divide them and see what happens. If you divide those, 4 lots of these makes that. So the peak that's probably come up is probably P4. 4 of them, and 31, because obviously, there's 4 of them. But the issue is remember that this is a mass spectrum, so it can only work if they detect positive ions, so it's got to be a plus there too. So now it says, give an equation for the reaction of phosphorus 5 oxide with sodium hydroxide. So unfortunately, you can't do P2O5, that don't work. That's not allowed. So it's P4O10. You've just got to really drill into your head that's what phosphorus 5 oxide is. And we're reacting sodium hydroxide, so NaOH, what do we get? Well, it's a salt plus water again, so it's Na3PO4 plus some amount of H2O. So then we need to actually do some balancing. So we've got 4 P's here, so I'm probably going to put 4 there just for a safe bet and see what happens. If we've got 4 Na3, we're going to need 12 of them. And then if we have 12 H's, we're probably going to need 6 of these. Does it all add up? Yes, it does. Next it says, draw the displayed formula of the molecule formed when phosphorus 5 oxide reacts with water. So if it's reacting with water, we need to figure out what it's making. So it's going to be making H3PO4, phosphoric acid. So what that means is that we've got to figure out some combination of this. So my best bet is you draw your phosphate, and I'm going to just draw my O here, and an O here, and an O here for now, because I know that they're probably going to be like H's stuck on here like this. Right, so now we have another oxygen left over, and there's no other H's to go, so we're going to have an O, but you can't just have a singular bond here, so that's got to be double. And also, this adds up, because it's in group 5, remember phosphorus? So 1, 2, 3, 4, 5. 5 electrons that it can form a covalent bond with. So, there's one of the phosphorus bonds making a covalent bond, there's the second one, there's the third one, there's the fourth one, and there's the fifth one. So that's how you get the structure. There you go. Enjoy. Okay, so table 4 shows the melting points of these 3 substances. Explain why the melting points of these are different. You should refer to the structure and bonding. So the amount of times I see people writing just all kinds of God knows what, of just everything, and not actually having any structure, to just give it a second to think what's going on, right? Literally describe what's going on first, and so on. So what I usually do is I get my thoughts straight. So I'm going to note form this, but obviously you turn it into actual words. NaCl, Cl2, HCl, right? So NaCl has the highest melting point. This is going to be the second highest melting point, and that's the lowest melting point, right? Now what you do is you compare it across the board, side by side. So if you compare this and this, what is different about NaCl and melting it? So when you're talking about melting and boiling points, you need to think what you're actually doing. So loads of people say, "Oh, you're breaking the bonds into blah 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 blah." Like, stop. Yeah. If you're melting something, you're breaking the bonds between what and what, not just bonds or the bonds. You need to say what it is. So if we're melting NaCl, you need to think what you're actually breaking. So in this case, it's the ionic bonds. So then you think, okay, how do I turn this into words? People say, oh, it's the electrostatic attraction between oppositely charged ions. That's great and all, but like, explain what that is here. So NaCl has a high melting point because it is a giant ionic lattice. But that doesn't explain why its melting point is high. You're just saying it has this structure. You need to say why. If it's got a high melting point, it means you need to put loads of energy in to actually melt it, which means you need a lot of energy to break the bonds. But you need to say what the bonds are. So it means lots of energy, highest energy needed to break bonds, oppositely charged, Na plus and Cl minus ions, because they are strong. Yeah, don't just say the bonds, or you gotta break the bonds. That's useless. Like, specifics, because 2 in 1, it means you'll never not get the marks. It means you're not going to contradict yourself by accident by saying random stuff, and it also makes you stick it in your head and remember it. So the next one is Cl2. Well, we need to think, what bonds are we breaking when we're boiling Cl2? Well, first of all, it's a simple molecule because it's just covalent compounds. So we're breaking the van der Waals forces between them. This is Cl2, so we're breaking van der Waals forces. So they're being broken, which require less energy because they're weaker than ionic bonds. We'll talk. So then that's that one. Then if we look at HCl, what bonds are in this? So we know it's, again, a simple molecule. It's got what? Van der Waals forces and permanent dipole interactions. So less E compared to ionic. However, hold on a second. We know that, you all learn that van der Waals forces are the weakest, then in permanent dipole, and then in, hydrogen bonds. So why is this higher than this? That don't make sense. So we need to think about what's going on here. So Cl2 has a higher melting point than HCl. Well, why? Think about it for a sec. So the only thing in this is van der Waals forces. The only bond you are breaking is the bonds between molecules. So it's the Cl2s and the Cl2s breaking apart here. You're not breaking the covalent bonds because you would end up with Cl and Cl, and that's not the same thing. So we're breaking the forces between the Cls and the Cls. So we're breaking the van der Waals forces only here. And we're breaking the van der Waals forces and the dipole interaction. So what people do is they'll try and go back to their brain and be like, where have I learned this in my notes? What have I done? What have I done? Just look at what you've written here. It must be that the Cl2's van der Waals forces must be stronger than HCl's, van der Waals forces and dipole interactions. It has to be. There's no other way to explain this. But then if you take a second to think, well, why would that be? What makes van der Waals forces stronger? It's because Cl2 has more electrons. So there's a stronger intermolecular van der Waals force and so forth. So that's how you deal with this question, is you do systematically, step by step, and compare each one, like for like, step by step. Because then it forces you to follow that thing and realize, oh, that's what it was. No point writing like 2 million flashcards on. This question is about some group 7 elements and their compounds. So chlorine is added to drinking water to decrease the risk of people suffering from diseases such as cholera. Suggest why the amount of chlorine must be controlled. Well, too much is poisonous. So don't just like say like, oh, toxic or whatever. Like, just actually explain why it needs to be controlled. Give an equation for the reaction of chlorine with water to form a solution containing 2 acids. So an acid is a proton donor. It's anything that can make an H plus appear on the other side. Don't just say proton donor. Actually understand that that's what that means. So the things that you should be familiar with is HCl, and the other option is HClO. So we must have HCl on this side plus HClO. We're reacting Cl2 with water because they've told you in the question. So that's that. So then we need to describe what this, why this reaction happens. You can't just say disproportionation. You have to say what that means. So what's going on here? We're going from one of the chlorines is going from an oxidation state of 0 to -1. So it's gained an electron. It's been reduced. But if you look here, that's +1. That's -2. That's got to be +1 as well. So that must mean that one chlorine's been that's been oxidized, and the one's been reduced. So one Cl reduced. And remember, when you talk about these, you must talk about electron movement. Which one's gaining an electron? Which one's losing an electron? Don't just say electrons are gained. What is? Don't use passive voice. So one Cl is reduced and gains 1 electron in HCl, and 1 Cl is oxidized and loses an electron to form HClO. A student bubbles chlorine gas through a solution of sodium iodide. State the observation that this student would make. So you should remember that chlorine will displace the iodide ions. So it's going to be NaI. It's going to eventually become NaCl because the chloride ions are going to be more likely to be there. So then you need to explain what the observation is. So have a think about what happens with the I. The I just doesn't just sit there. It eventually becomes I2 again. So now you've gone from something with no I2 to I2. So what you make is you form either a brown solution or black solid. Either's fine because of the I2 forming. So then we need to look at the ions that. So what we started with I minus. We end up with I2. We need to think about why that's happening. What's making it happen? Well, Cl's come along and become Cl minus, hasn't it? So we're going to have that there. So now we need to balance this. If we've got I2, it's going to be 2 there. If we're making Cl minus, well, this is being oxidized to form I2. Something else has to be reduced. So what's gone in has to be chlorine to get reduced. So it means we must have Cl2, which is what it exists as. There's got to be a 2 there as well. And that's what the ion. The student adds a few drops of concentrated sulfuric acid to a small amount of sodium iodide. 2 gaseous sulfur-containing compounds are produced. Give an equation for the formation of each of these sulfur-containing products, and then state the role of sulfuric acid in the formation of these. Unfortunately, there's no hack around this. Unfortunately, just sitting and memorizing these dang equations. So it's in steps. It's a stepwise thing. So what's going on here? Give an equation for the formation of each of these things. So you should remember that in these reactions, what's going on is that you're going from H2SO4 stepwise down to eventually H2S. So the first equation is going to be our H2SO4 forms SO2, right? That's equation 1. And equation 2 is going to then be H2SO4 is eventually completely gone down because it can do either 2H2S. Now it's told you that you're adding sodium iodide, and they want they want ionic equations as well. So then what we're going to do is we're realizing that we're going to add iodides. So it's going to be, you're going to add your I minuses. And what do we make on the other side? So if it's an I minus and it's eventually going to become an I2, well, off the bat, we need to know that there's going to be two I minuses there. Think about what's going on in terms of electron movement. So each one of these is losing an electron to form that. So that must mean that this is gaining electrons itself. So in order to balance it out, like your other redox half equation-y stuff, balance everything out as you would, with the oxygen stuff. So we balanced all the elements are nearly balanced. The oxygens aren't, so we can add waters on this side. So we've got two O2s dealt with, but we have 4 on the other side. So we've got two oxygens there, but we've got 4 on the other side. So we're going to add 2H2O here. And then we have, how many? We've got, what's that? 2H2s here. So that's 4 H's, but 2 here. So we're going to have to add, 2 H pluses there. That's when we're doing it. Alternatively, you can write the whole equation out, but I'm just doing this because it's... So then, for the other one, it's H2SO4, and you're making H2S, but then you're also going to make I2. Because you're reacting again with I minuses from the sodium iodide solution. So now we need to figure out how this is all going. So each one of these electrons, again, loses 1 electron to make this. But we need to figure out how many electrons this is getting. So we're going from what? So that's going to be -8 plus 2, so +6 as an oxidation state, to -2. Right? So if we're going from +6 to -2, it means that this sulfur needs to gain 8 electrons, and that all comes from here. So that means this is giving away 1 electron, and we need 8 of them. It's going to be 8 here. So that means we've got 8 there, we've got 4 I2 there. And then we just do the same. So the sulfurs are balanced out. We want to do the waters now. So we've got 4 O's there. So it's going to be 4 H2O on this side. And then because we have what? How many is that? So that's 4 H2O. That's 8 H2s. But then we also have 2 here. So, sorry, that's 8 H's, but we have 2 already here. So we're going to need 8 H plus on this side as well. So that's one way of doing it. Alternatively, you can just regurgitate the equation. So then it says, state the role of sulfuric acid in the formation of these products. Well, sulfuric acid is getting reduced, but it's causing something else, the I minus, to be oxidized. So it is an oxidizing agent. So the student adds a few drops of acidified silver nitrate to a solution of an unknown impure sodium halide. The student observed bubbles of gas in a colorless solution. The student bubbles the gas through a calcium hydroxide in a white precipitate. Forms deduce the identity of this sodium halide, suggest the identity of the gas, and then write an ionic equation for this gas out from the impurity. So off the bat, you can see it's going from calcium hydroxide in a white precipitate. So this gas must have been CO2 because it's the milky white thing that happens when you bubble it through lime water. So then what are we doing? So we're adding silver nitrate to an impure solution of sodium halide, and then you get bubbles of gas in a colorless solution. So again, if you're adding silver nitrate to a halide, you've got to remember that you can get precipitates forming. So for example, your AgBr, AgI, and so on, and the yellow and so forth. So we've got a colorless solution here. If it's colorless solution, then it can't be a sodium chloride because that makes a white precipitate if you have AgCl. Can't be bromide because it's cream, and it can't be iodides because it's yellow. So it's got to be fluoride. So the sodium halide has to be NaF because it's still reacting, but there's no precipitate made, and that's the only one that doesn't make a precipitate. The identity of the gas, like we said, must have been CO2. So there must be some weird reactant in here that eventually makes CO2, like something in there that's an impurity. So let's have a think logically what's going on. So what they've done is they've got acidified silver nitrate. So they've added an acid to make CO2. So whatever this thing is probably a carbonate, some sort of carbonate salt. So carbonate plus an acid makes the salt plus water plus CO2 plus H2O. But they want an ionic equation, so the salt doesn't really matter here. It's the H2O that's made, and then the other stuff. So CH2 plus H2O. Well, the CO2 must have come from the carbonate ion, which is CO3 minus. And the H must have come from the acids, so that's going to be H plus, and there's 2 of them, so it's going to be that. So then it says the ClF2 plus ion contains 2 group 7 elements. Use your understanding of the electron pair repulsion theory to draw the shape of this ion. And then include any lone pairs of electrons that influence the shape. Explain why the ion has the shape you have drawn and suggest a value for the bond angle. Okay, so think of it step by step. So Cl is in group 7. If we draw. So that means we've got 1, 2, 3, 4, 5, 6, 7. Now, ordinarily, when you're making Cl, for example, F, it can make it one, you get one for the electrons from the F here to make a covalent bond. But because you can see there's a ClF2 and it's a plus, if we added another F, for example, here, and there was another shared pair electron and a covalent bond, the whole thing, this Cl would be like negative. So it's evident that this Cl must have given away 2 electrons to an F as well, for it to be short of an electron overall, if that makes sense. So like this F can't, 2 of these must have come from the Cl, and this F didn't provide its own. So that means this is what it must look like. So that means its shape is like that. And we have 2 bonding pairs, 2 lone pairs. So then it says, well, explain why it's the shape it is. So it's because, and it's always this. So lone pair is the biggest repulsion, then lone bonding, then bonding. And then the angle, well, it's just memory, unfortunately. You can have 104 to 106, whatever you memorized it as. Magnesium is used in the extraction of titanium from titanium IV chloride. Give an equation for this reaction. So we're going from TiCl4, because it's titanium 4 chloride. We're using magnesium, and we're extracting titanium. So it's going to be Ti on the other side. So then what we got to do is figure out what's happening with the Mg. So the Mg is probably going to be making, I've not got enough space, plus MgCl2. But we have 4 chlorines at the start, so we're going to have 2 MgCl2s here to balance that out. So we must have 2 Mgs. So copper complexes are colored. The color is caused by the d electrons moving from their ground state to an excited state. Explain why aqueous solutions containing CuCl4 2- are yellow. So the amount of people that will just jump straight to say, okay, transition metal, and completely stop. All it is saying is, why is this solution yellow? So if you see a black object, it means all wavelengths of light, so wavelengths of colors, all the colors are being absorbed, nothing is coming back to you. If you see something that is white, everything is coming back to you. So the reason plants are green is because what's going in is all of the white light, all the light you can have. They take in everything, but what comes back to your eye is green. They're not absorbing the green, which is why it's green. So if this is yellow, what it means is that this is absorbing every single color except yellow. So all wavelengths of light except yellow are absorbed by the electrons. The yellow is reflected, and that's what gives it its color. It's got nothing to do with, it can be desubject, blah, blah, blah. Like, understand what the question's asking you. Then it says, when a d electron moves from the ground state to the excited state in a copper complex, the energy changes this. The Planck constant is that. Work out the frequency of the light absorbed. So the energy gap change is going to be E equals HV, or E equals HC over lambda. So then that means that if E equals HV, then delta E over H can give you V, which is going to be 3.98 times 10 to the minus 19 joules over the Planck constant, which is 6.63 times 10 to the minus 34 joules seconds. Can you see how this would give you a unit that's in joules per second? It's a bit irritating because this is E equals HF, which is the frequency for all my physics fellows. So that'd be 6 times 10 to the 14. So state 3 ways in which a transition metal complex can be changed to alter its color. So what you got to remember is that transition metals, d orbitals are chilling like that. 1, 2, 3, 4, 5. Sorry, yeah. Then what happens is when some ligands bind to it, what can change is that it splits them into these. So you've now got the same d orbital split into 2, but the energy is a little bit higher, so it can go up and down. That happens when the ligand bonds. Otherwise, it's just chilling on its own. So if the ligand is bonded, making that happen, by default, it's things that screw up the ligand. So if you change the ligand, that will happen. But however, it's whatever affects the degree of that can also depend on other things as well. So for example, the oxidation state of the metal, because that means then the behavior of the ligands that are attached to it, even if you have the same ligands, are going to be different because the oxidation state of the metal is different, and also the change in the coordination number as well, because those are differing numbers of ligands. So a lot of them is just to do with the specifics ligands wise, because they're the ones that determine that energy gap predominantly. So it says consider the following reaction scheme in which P, Q, and R are different complexes of iron. So you got CuCl4, you add excess water, you make some aqueous thing, and then use EDTA, and you get this aqueous R thing. So then it says, excuse me. So then it says name the shape of the CuCl4 2 minus ion. So it's a transition metal complex, and it has how many coordinate bonds? It has 4 coordinate bonds, and it's not like platinum, so it's got to be tetrahedral. So then it says give an ionic equation for the conversion of CuCl4 2 minus to complex ion P. So look at what the question's telling you and just work off of that, and you can probably solve a lot of these problems. You don't have to dig in your head and be like, oh, what kind of equation must this be? So we start with CuCl4 2 minus. They've told you they're adding some excess of water. And then all you got to do is just figure out what might be happening. So if we look at what might be going on, we're making some sort of thing that's this is aqueous thing that's P, and it's able to react to the EDTA. So this clearly, whatever's left behind has to be some sort of complex ion that's a ligand. It can't like form a salt. So your best bet is that these H2Os are probably swapped. It's a ligand substitution reaction. So you've got Cu, H2O, 6,2 plus. So then you're left out with the 4 Cl minuses from here. So now all you got to do is put 6 H2O there. So then it says, state the color of the solution containing complex ion Q. So what are we doing with that? We're adding excess aqueous ammonia. So when you do that, you get a partial substitution reaction where some of the Cu, so if we had CuH2O6, two of the H2O stay, but 4 of them become NH3s. So in this case, what's going on here is that we've probably got the same thing happening where some of those Cl4s are switched for NH3s, but remember the H2Os also have to come here as well. So the color change that you end up getting is that it goes deep blue. So you're starting with CuCl4 2 minus. That's what we definitely know is happening. We know that we're adding some amount of ammonia, and we know that the end product has to be that complex where you've got that partial substitution. So NH3 4 H2O 2 plus 4 Cl minuses. They've all been booted off. They've been substituted off. So we need to get the H2Os in there, we've got to add H2Os here as well. There's 2 of them, so there's got to be 2 there, and we've got to have 4 NH3s there. Done. Then it says identify the complex ion R. So it's just CuC, there's some sort of copper ion with EDTA. So it's got to be CuEDTA like this. And then we've got to figure out if it's got a charge. Well, it tells you that there's Na4 EDTA, so that means it's each Na is 1 plus. So there's 4 of them, so it's got to be 4 minus, but the Cu is 2 plus, so it's got to be 2 minus overall. So this question is about fuel cells or cells and stuff. A lot of the time you can just look at what the page is saying and work off of that, and then you can work backwards. You don't have to remember loads and loads and loads of bits and bobs. Obviously there's some remembering, but like a lot of the time it's doable with what you got here. So the half equations for 2 electrodes that combine to make a non-rechargeable cell are Zn2 plus and 2E minus gives you Zn, and then on and so forth. So it says identify the oxidizing agent. So if something is an oxidizing agent, it means it itself is getting reduced and oxidizing something else. So if that's the case, then, well, that's the first one's being reduced. We need to look at the second one. The MnO2, what's that? That's plus 4, and it's becoming, what's that? Minus 6, plus 3. So it itself is being reduced, which means something else has to be oxidized. So that is the oxidizing agent, MnO2. Because, again, you can't reduce one thing without oxidizing another. Figure 1 shows a cross-section through a rechargeable zinc-silver cell. Suggest the function of the porous separator in figure 1. Now, obviously, you might not know this exact cell, but you've got to remember the basics that make a cell function. So you have 2 electrodes, you have the outer circuit, but then you can't have it work unless the circuit is complete. So let's have a look at how this thing works. So you've got an AgO2 paste here, because that's the silver. And then we've got a mixture of the zinc and an electrolyte. And you've got a porous separator. We've got metal and insulation. So the porous separator must be something to complete the circuit, otherwise it wouldn't work. So it's got to be, you could say, for example, it could complete the circuit, or it could be a salt bridge. Because if we look, it would be like this, the flow. So then it says the standard electrode potentials for 2 half equations of the silver zinc cell are these. Give an equation for the overall reaction when the cell is recharged. The amount of times people get caught out by this is just wild, because they don't know what they're doing in the following routines. So ordinarily, yes, in a normal scenario, you would think, oh, well, that's being oxidized. This one must be reduced. However, that's if a cell is discharging. When you're running a cell normally, it is discharging. It's doing its thing. When you're recharging it, you're flipping it the other way. You're running the circuit in the opposite direction. So what's actually happening is that this is being oxidized and this is being reduced. Because the question wants recharging, not discharging, or just when the cell is run. When the cell is run, it's discharging. Because you're oxidizing it, you're actually running it the way around. So that's where people get caught out. So all you gotta do is match the electrons, but write them the right way. So this one's being reduced. So therefore, since the bottom one's reduced, that's gonna stay the same. So that's gonna be ZnO solid. Forget the electrons because we're combining them. And then obviously this one's gonna be flipped. So the H2Os are gone as well. So at the same time, obviously you can do it step by step if you want, but I'm just doing it fast here. Ag solid, because that's on the other side. The OH is on this side, but we flip that, so it'll be on the other side. That also disappears. So then the ZnO becomes Zn solid plus Ag2O. Alternatively, you can just put them together and then cross them out. I'm just doing it in one step. But again, it's that bit that I see get caught out time and time again. The EMF of an alkaline hydrogen-oxygen fuel cell is 1.23 volts. The standard electrode potential for one of the electrodes in the alkaline or hydrogen-oxygen fuel cell is as follows. So you got the H2O, the 2E minus gives you the OH minus, and the H2. That bit explains the alkaline part, and this explains the oxygen. No, sorry, it doesn't explain that. That explains the hydrogen part, but I don't see oxygen here. So even though, yes, you could go and learn the formula and memorize it and stuff like that, off the bat, it says alkaline oxygen, hydrogen oxygen fuel cell. So alkaline again, OH minus, hydrogen's here, oxygen's not here. So the other one's got to have oxygen in it. So based on that, what that must mean is that this has to have oxygen in it. So you know that that should then rejig your memory to be like, oh, well, in that case, it's got to be the other one that's 2H2OL plus 4E minus gives you 4OH minus aqueous. So in an alkaline fuel cell, that's what that is. So then it says give the half equation for the other electrode and calculate standard electrode potential. So the EMF for any cell is E reduced minus E oxidized. They've told you that the overall thing is 1.23. We now need to decide, obviously, because these are both written in reduction form, you have to remember which one's being reduced, which one's being oxidized. So in an alkaline fuel cell, the oxygen reaction's happening at the positive electrode, which means that's the one that is being reduced. And in the negative electrode, you've got this other one up here, and that one's being oxidized. So what that means is that the reduction is going to be the one we're looking for, X minus 0.83 volts. So that means, because that's a plus, 1.23 minus 0.83 will give us X, which gives you plus 0.4 volts. So then it says, suggest where the EMF values of the acidic and alkaline hydrogen-oxygen fuel cells are the same. Well, again, EMF equals the potential of whatever's reduced minus the potential of whatever's oxidized. Whoops. So if we ran this in the opposite way, we would just be flipping the signs of these. So if we because remember that acidic and alkaline ones are the opposites. So if I did it the other way around, if I said, okay, fine, let's say that we said that the reduced is what the the 0.4 we just worked out. Let's do it the other way around. So what's oxidized now is minus 0.83 minus 0.4. It would be minus 1.23. So it's the exact same, just flipped around. Why? Because it's the same overall equation. So although, yes, it's a minus, it's just the size of the EMF is the exact same. Right. Enjoy. Hope that helped. Thank you. Please like and subscribe. And also add a thank you so much, like and subscribe as well to the other video, please.